Okay, so today we're going to talk about light. Light can travel like a wave. It propagates through space and time. And so think of the point source as the source of light, and the light radiates from that point source. And as it propagates through space and time, what it does is it kind of travels like a ray, and it also travels like a wave. So the distance from peak to peak we call a wavelength. So from here to here, that is one peak to another peak, which is the wavelength, or how we see colors of light. And then there is a wavefront, which is like a plane. So plane wavefronts are just basically measuring peak to peak of the waves as they travel or propagate through time and space. And so for a plane wave, the wavefronts are planes, and from a far enough point source, the waves are approximately planar. So we'll talk about light being planar. And it just means that the light source is far away. So a lot of times it's easier for us to do our calculations if we consider planar light. So anyways, when we see objects, it's because there are light rays that are reflected off of them. So a light source hits this rabbit. The rabbit reflects the light, and that is what our eye receives, is the light reflected off the rabbit. Likewise, light can hit a rabbit. It can hit a mirror. The mirror bounces that light into our eyes, and then the image we see would be what we call a reflection. And it could be virtual or it could be real. So there's some basic rules about reflection and refraction. The first thing I want to talk about is the angle of incidence. So if I have a surface that is being hit by planar light, as the light ray comes in and hits the surface, if I draw a normal line, in other words, if I'm thinking of a line that has a 90-degree angle with the surface, and I measure the angle from that normal line to the ray, I would call that the angle of incidence. And so for light, the angle of incidence is always equal to the angle of reflection on a smooth reflecting surface. And so theta sub I should always be equal to theta sub r. So specular reflection is a reflection across a smooth surface. When a light source hits something, it's usually more than just one ray. So just think of several rays hitting a smooth surface. The angle of incidence will always equal the angle of reflection, and so this will happen a lot. Now, not everything is a smooth surface, so sometimes light can have what we call a diffuse reflection, which is just a reflection from a rough surface. So now what happens here is that because the angle of the smooth surfaces where the rays hit they vary, that means that'll have an impact on our angle of incidence, because the incidence is the angle from the normal line of the smooth surface that the ray is being reflective off of. So here, the angle of incidence is greater than the angle of incidence here, and the angle of incidence here is a little bit different. So you get some funny stuff that happens with a rough surface. We can reflect rays by drawing diagrams. And so basically, if this is my surface here, m sub 1, and my ray comes in with an angle of incidence of 60 degrees, then I know that my angle of reflection is 60 degrees. And if this is a 90-degree angle, then my second surface should also enter in an angle of incidence of 60 degrees. And so on and so forth. So as we, 30 degrees, because this angle here should be 30 degrees. And so I get 30 degrees here. So we can use this concept of angle of incidence equals angle of reflection, and reflect a light in several different directions, which will be useful when we make our solar cells. So refraction occurs because the speed of light is different through different media. So as that light propagates, if we go back a couple slides and we talk about how light radiates or propagates through space and time, light is an electromagnetic radiation, and it propagates through space and time like a wave or like a ray. Imagine if I dropped a pebble in a pond, I would get this wave pattern. But then imagine again if I dropped this pebble in a pond of motor oil. I would still get this wave front, but it would move at a much slower rate because of the properties of oil. So when we fast forward here and we talk about Snell's law, because light travels across a boundary from one media to the next, it bends because it changes its velocity or how it can propagate through the medium. And so this is the mathematical relationship. And so to get a picture of that, light is refracted when our incident ray has an angle, an incident angle to the normal of the boundary in medium 1, and then the angle, the second angle, is proportional to the index of refraction of the medium. Now, where we get the index of refraction of a medium is that the index is equal to the speed of light over the speed of light in the medium. Now, the speed of light in a vacuum is 3 times 10 to the 8th meters per second, and there's really nothing to slow the light down, so that's the fastest light can propagate. However, when you travel through a medium, it's going to slow down. So your number here on top is always going to be bigger than the number on the bottom, which means that the index of refraction will always be equal to 1 or greater than 1. So here's a list of some indices, and so using the formula, the actual wavelength in the vacuum divided by the indices will give you the change in the wavelength. And basically the frequency of the wave stays the same, but the wavelength of the light is shorter where the index of refraction is greater. So remember that the frequency of a wave is inversely proportional to the wavelength. So the wavelength changes a little bit where the frequency remains the same. So here is the index of air, which is almost 1. So light traveling through air is almost at the speed of light, but it does slow down a little bit. Water is 1.3, ice is 1.31, and so on and so forth. When you get into some of the denser materials like diamond, it's 2.42. So if I were to plug that in here, I'd have the wavelength, and I would divide that by 2, which means I would almost cut the wavelength in half. So there's some interesting things that take place when we go through different mediums. So if I take those indices and I use Snell's law, one way to rewrite Snell's law is the index of medium 1 times sine of the angle of incidence through that medium should be equal to the angle of incidence of sine as it goes through the second medium. So usually in our homeworks we'll get 3 out of the 4 and we solve for the 4th, or we'll be given a clue. So what happens is as the light is in medium 1, it passes through here, and then if I take the index times the sine of theta 1, that will have an impact on where the light bends in the second medium. So if the second medium has a greater index of refraction than the first, the light bends inward towards the normal. However, if the index of the second medium is less than the first medium, then it'll bend away from the normal. So here we have an example of air and glass and light. So this is kind of how a prism separates white light into the different colors. So if you applied Snell's law twice, you have an angle of incidence that comes in this way. And then mathematically, based on the change in the indices of the mediums, it gets bent towards the normal. But some light does pass through, which is the original path and the new path. And so the interference patterns kind of separates it into different colors. That's how a prism works. So mirages can be formed by light refracting through the air of different temperatures, which means there's different densities. So what they're saying is as we're closer to the surface of the Earth, the air is warmer, but as you go up higher, the air is cooler. And so that does have an impact because of the density of the molecules that are in the air. And so you'll see kind of a mirage from a distance. And it's all part of Snell's law. So refraction can distort underwater views and make straight objects appear bent, make submerged objects seem shallower than what they really are. So for example, if you're, this last example is a pretty common one. If you look into the water because the light gets bent, the penny appears to be closer to the surface than what it actually is. Here's a picture of a straw. Depending on the angle that you look at, it looks like the straw bends in the water, but really the refraction based on Snell's law gives that appearance. Same with when you reach into a fish tank to, I don't know why you would grab a fish, but if you were to reach into water to grab something, it takes a second to try to figure out what you're grabbing and how. So refraction can occur through the atmosphere and can make the sun appear flattened at sunset and increase the length of day. So what that means is that the sun is actually here, the light rays are coming as they enter into the atmosphere, they get refracted or the angle is changed, so then the ray of light, instead of passing over the earth, actually stays and kind of hangs around. That's why at sunset you could still kind of see light even though the sun may no longer be visible across the horizon. So what that means is that the sun appears to be here, but in reality the light is bent as it enters into the atmosphere. So total internal reflection in fiber optics occurs when the light basically, when entering a medium of lower index of refraction, the refracted ray bends away from the normal. If the incident angle is large enough, the angle of refraction is 90 degrees and no light escapes. So if what they're saying is as this light comes in and it bends, if it's large enough, then all of the light is reflected instead of refracted. And that can occur. So for an angle, if I wanted to calculate that angle, what I would do is I'm going to take, to find the critical angle, I would say sine of the critical angle is equal to the index of the second medium over the index of the first medium, and that will give me the angle that I need to shine things. So here, if we jump back, we just have water and air. And so if I shine the light at a small enough angle to the normal, it just gets refracted and some of it gets reflected. If I go to a wider angle of incidence, then what happens is some of it gets reflected and some of it just kind of stays along the boundary because of the angle of refraction. If I do it right and I get the right angle, I get a total internal reflection. And the way that I would calculate that critical angle is this here. So then total internal reflection is how fiber optics works. You can transmit a signal of light and keep it bound inside a fiber optic cable. And they're just manipulating the indices and angles in such a way that the light just kind of reflects and reflects and reflects through the fiber optic cable forever. Internal reflection prisms are used in binoculars to keep the length short, is one example. Another thing to think about is like a diamond. The reason diamonds shine so brightly is because of the angle that they're cut at. They keep a lot of light internally. So before the light escapes, it really kind of bounces around inside the diamond, which is why they shine so much. Now, true fiber optics, the way that they're designed is their total internal reflection just kind of guides the light along a path. So that no light is really lost. None of it comes outside of the fiber. So if this was like a fiber optic, the light just kind of bounces on the inside. If you bend that fiber optic, the light just kind of bounces on the inside, and no matter how you bend the fiber optics, the light just kind of bounces. So this is like an image of like a laser being pointed through a fiber optic cable. So we can simulate this in a way. A great way to simulate this is to shine a light through a water source, because the water can sometimes keep the light reflecting inside of itself. Or if you take like a thin plastic and shine the light through a thin plastic, it gives a similar effect. So the reason the tips of these thin plastic tubes are so bright is that the majority of the light, which is usually like a light source down here, shines into the tube, and then the light is reflected back and forth throughout the fiber optic, and then it'll come out the end. So dispersion occurs when the index of refraction depends slightly on the wavelength. So what we can do is we can manipulate the medium that the prism is made out of and the angle of incidence in such a way that we separate white light into various wavelengths because of the angle in which we see them. So dispersion on a prism takes white light and separates it and changes it into different bandwidths, because as the white light hits here, it changes the wavelengths, and as those wavelengths enter or exit the prism, you have refraction again, and that changes the angle and the wavelength a second time. And so what you'll do is you'll literally separate the colors of visible light. And so dispersion of sunlight in small drops of water can produce a rainbow. And so what you're really seeing is that if you have one drop of water, so this is why we see rainbows when it rains outside, there's enough moisture in the air usually still that the light that you see gets refracted. And depending on where you're standing and where you look, you'll get different colors. And so if you look from top to bottom, you'll see the colors of a rainbow from red to violet.